Says lesson number 4, but that's because I stole it off someone, another physics teacher out there. He's good with that. I checked him. The big misconceptions. So, what's the big deal? Many people have known Newton's first law since 8th grade or earlier. Which is the first one? Objects in motion. Everybody knows that. If prompted with the first few words, most people could probably recite the law word for word. And what is so terribly difficult about remembering that F equals ma? It seems to be a simple algebraic statement for solving story problems. In fact, I would go so far as to say that it's a law, something that is used to predict, something that we see over and over again, right? A law. I mean, it is, after all, called Newton's second law. It just happens to be a mathematical one. The big deal, however, is not the ability to recite the first law, nor to use the second law to solve problems, but rather the ability to understand their meaning and to believe their implications. While most people know what Newton's laws say, many people do not know what they mean or simply do not believe what they mean. I would even go so far as to say, is that they might know what they mean, they might believe it, they don't know how to apply it to another situation, which is ultimately what one of my goals is to get you to that point where you can apply your knowledge to a new and novel situation. If I say an object in motion, people say stays in motion. They can give it back to me, but they can't sort of apply it to new knowledge, okay? And really, well, we're getting on this in the next paragraph. Maybe I'll just wait till I read through this here. Cognitive scientists who study how people learn, have shown that physics students come into physics class with a set of beliefs which they are unwilling or not easily willing to discard despite evidence to the contrary. These beliefs about motion, known as misconceptions, hinder further learning. So you come in here, you think you know something, and then it's my job to sort of, well, really prove you wrong. Do people like being shown up to be proved wrong? No, not necessarily. People don't like it when their beliefs or their explanations or their thinking, their theories are shown to not be wrong, and they're unwilling to change. I said this morning, I was going to say, and then I backed off a little bit, I was going to say this morning, teenagers tend to not like to change. But then I would sort of talk it through with the class, and then I came up and said, you know what? I think there's people of all ages that don't like change. Would you agree? Old people too? People my age? I didn't say old people. People don't like change unless it's at the source, right? Especially when it's something that you believe.
Even then, some people just don't like change.
Oh yeah, that's true. They just throw it in there. They throw it in a little container, right? Right. So you will likely be confronted today, and you have been the last couple of days, confronted with some thinking that hasn't fit with your thought process, right? Your beliefs, and you might be challenged by that. All right. The task of overcoming misconceptions involves becoming aware of the misconceptions, considering alternative conceptions or explanations, making a personal evaluation of the two competing ideas, and adopting a new conception that is more reasonable than the previously held one. Think back to like the whole idea about the sun being at the center of the solar system, or the Earth, right? People, we all know, believe the Earth is at the center of the solar system, and when they were proven wrong, they had a hard time with that. They took people that believed that and burned them at the stake and put them in house arrest and did horrible, unspeakable acts to them, all because their belief system was challenged. Now, I'm obviously not going to burn anyone at a stake in here today. Well, I might. And I would even say that the law of parsimony, remember that from a few weeks ago, was the law of parsimony. The simplest one is like the truth. Well, I would sometimes argue that that works against us, and that people want a simple explanation, but that's not the truth, right? So there is that as well, I guess you could say. Okay. This process involves self-reflection to ponder your own belief systems, critical thinking to analyze the reasonableness of two competing ideas, and evaluation to select the most reasonable and harmonious model which explains the world of motion. Self-reflection, critical thinking, and evaluation. While this process may seem terribly complicated, it's simply a matter of using your noodle, your brain, thinking, and going along with it too. Okay, so here we go. The most common misconception is one which dates back for ages. It is the idea that sustaining motion requires a continued force. What was the key word out of yesterday? Remember I ranted and yelled? What's the one word that I said over and over again? Equal. And yet, equal. And yet, People still, there may be some in the room still that when I ask, like when the bug hits the windshield, which force is greater? Equal. Right? And you still might be having a hard time letting go of that. The idea that sustaining motion requires a continuing force. The misconception has already been discussed in a previous lesson, but we'll now discuss it in more detail. This misconception sticks out its ugly head in a number of different ways and at a number of different times. And will I test you on it?
Yes.
Yeah. Will it be a new and novel situation that you've never seen before? Yes, you'll have to apply your knowledge. As you read through the following discussion, give careful attention to your own belief system. View physics as a system of thinking about the world rather than information that can be dumped into your brain without evaluating its consistency with your own belief systems. In other words, it's not the answer that matters so much. Don't worry about just getting the answer. Newton's laws declared loudly that a net force, I'm just going to make a space here because I'm having a hard time reading. Newton's laws declare loudly that a net force, an unbalanced force, causes an acceleration. A net force causes an acceleration. You might at one point, I might have said to you, a force will cause, you might have said motion. I'm applying a force, no motion. Is there an acceleration though? Person on the table has a balloon. How come? Because it's got to be a net force, an unbalanced force. That force is balanced. Unbalanced forces cause acceleration, which is a change in motion. The acceleration is in the same direction as the net force. To test your own belief system, consider the following question, and its answer is seen by clicking the button. Obviously, you don't have a button there. Okay, so I'm going to ask, it's a single question. I didn't bother with clickers because for one question it doesn't matter. Okay, are you infected? So here we have a picture over here. Two students are discussing their physics homework prior to class. You guys probably do that all the time. They're discussing an object which is being acted upon by two individual forces, both in a vertical direction. Vertical means up and down. The free body diagram for the particular object is shown at the right. Now, I'm doing things a little bit out of order here. We'll talk more in depth about free body diagrams near the end of this period. Okay, but rest assured, it's just a diagram. Okay, so right here, I've got a force down of 20 newtons, and I've got a force up also of 20 newtons. Are those forces balanced? They are. 20 and 20. During the discussion, analytical. Pause for laughter. Like that one? I didn't write it. Analytical suggests to know a formula. See, that's a good one, eh? Analytical suggests to know a formula that the object under discussion could be moving. So analytical says, Anna could be moving. She suggests that it could be moving. In fact, Anna suggests that if friction and air resistance could be ignored because of their negligible size. What does negligible mean? So small that doesn't matter, like pennies. The object could be moving in a horizontal direction, left or right. According to Anna, an object experiencing forces described to the right could be experiencing a horizontal motion as described below. Noah formula objects, arguing that the object could not have any horizontal motion if there are only vertical forces acting upon it. He's saying that because the forces are only up and down, it cannot be moving sideways. Noah claims that the object must be at rest. Must be at rest. Must be at rest. Okay. So Noah says, let me just summarize here again. So Anna says it could be moving. Noah says it must be at rest, right? Noah claims that the object must be at rest, perhaps on a table or floor. After all, says Noah, an object experiencing a balance of forces will be at rest. Who do you agree with? Okay, so I'm going to give you a few seconds to think. If you want to talk it over with your neighbor, you can, but you have to vote. You're either going to vote for Anna or you're going to vote for Noah. Anna says could be moving. Noah says must be at rest. Who votes for Anna? Who votes for Noah? Ooh, well, half and half. Could be moving. Could be moving because, hey? If the object, okay, you can, yeah, now it's time to listen. If the object was already moving, right? Objects in motion stay in motion. So if it was already moving, then it just keeps on moving. It doesn't. It doesn't say that. But it says, she said it could be moving. He said it must be at rest. If he had said it could be at rest, would that be true? Because it could be at rest. But he said it must be. So that's the difference. I wrote it right there. Must be right there. Okay, so remember last winter when you went sledding down the hill and across the level surface at the local park? Who's been to Durston Hill? Right? I think they tamed it down a little bit, right? Oh yeah. Durston Hill? The big toboggan hill? Yeah. That's pretty crazy. It used to be like really bad. Anyways. Okay, so you're sliding down Durston Hill and at the bottom it gets flat, right? Imagine for a moment, that there was no friction along the level surface from point B to point C and that there was no air resistance to impede your motion. How far would your sled travel? Only to C and then stop? Okay, Jared and Noah, I need you to listen. In fact, the sled, if it was frictionless and there was no air resistance, it would go forever. Exactly. Objects in motion stay in motion. Like that's what that means. How far would your sled travel and what would its motion be like? Most students I've talked to quickly answer. The sled would travel forever at constant speed, without friction or air resistance to slow it down. The sled would continue in motion with the same speed and in the same direction. The forces acting upon the sled from point B to point C would be the normal force, the snow pushing up on the sled, and the gravity force. See the diagram? Right? So this is exactly the same. And I haven't talked to you about gravity, and I haven't talked to you about normal forces yet, but we will. These forces are balanced, and since the sled is already in motion at point B, it will continue in motion with the same speed and direction. So, as in the case of the sled, and as in the case of the object, which Noah and Anna are discussing, an object can be moving to the right, even if the only forces acting upon the object are vertical forces. Forces do not cause motion, forces cause acceleration. So let's just highlight that. Forces do not cause motion, forces cause accelerations. Okay? Why do people generally get this wrong or backwards? Well, because they're used to, if you want to keep something moving, like if I'm pushing this chair, and I want to push it all the way to the back of the room, I have to keep pushing it. How come? Objects in motion, supposed to stay in motion. I'm supposed to be able to do that and keep going forever. There's friction, and that's why, because there's always friction. Friction always, friction always is there, and so we have to keep pushing. Okay? So it's not what we generally observe. Newton's first law of motion declares that a force is not needed to keep an object in motion. Slide a book across the table and watch it slide to a rest position. The book in motion on the tabletop does not come to a rest position because of the absence of a force. Rather, it is the presence of a force. What force is that? Friction. Friction. That force being the force of friction, which brings the book to a rest position. In the absence of a force of friction, the book would continue in motion with the same speed and direction forever, or at least to the end of the tabletop. A force is not required to keep a moving book in motion, and a force is not required to keep a moving sled in motion. Force is not required to keep any object, horizontally moving object in motion. Okay, so I'm going to walk you through free body diagrams, how to draw them, and then you're going to have an opportunity to try some on your own. Okay? Is that a little small to read? Let's make that you can read that? Let's make that a smidge bigger here. Free body diagrams are otherwise known as FBDs, are simplified representations in a problem of an object, the body and the force vectors acting on it. This body is free because the diagram will show it without its surroundings, i.e. the body is free of its environment. This eliminates unnecessary information which might be given in a problem. Taz, are you listening? Let's take this figure to be a pictorial representation of a situation, a sled on snow with horses pulling. First we need to represent the sled, which is the body in our problem, as a really simplified figure, a square resting on a flat surface. Most textbooks will draw a little box. Some of them just use a point, just like a single dot. There is some discussion as to whether or not there should be the floor here. Some books will not draw the floor because they say that it's not free of that. I'm thinking, in my mind, it doesn't matter a whole lot. If it makes you understand better, go right ahead and draw the floor there. In this tutorial, we'll review some of the main forces which you will encounter in physics and discuss their contributions to an FBD. And as I said before, then you'll have a chance to practice. So, first one, gravity. First force we'll investigate is that due to gravity, and we'll call it gravitational force. We know that the acceleration due to gravity, if on Earth, is approximately 9.8 meters per second squared. And the force by Newton's second law is Fw is equal to m times g, which is really just F equals ma, where the g is the acceleration due to gravity, right? So g, the gravity, is a form of acceleration. Braden, you all right? And it was the mass of the carriage. Let's add this to our diagram. So you already have it added. I'm just going to redraw it right here. So we draw it down like that, and I like to label it Fw. Some books will label it Fg for gravity. A couple different ways of doing that. Some books draw the arrow, the force vector, from the middle. Some of them draw it from the bottom like that. It doesn't make any difference. It's just a convention. Note that the force vector labeled Fw or Fg points downward, as this is the direction in which gravitational force acts. Will it always be down?
Yes.
Which one? Gravity. Will gravity always be straight down?
Yeah.
Always?
No.
Gravity acts down. Gravity acts down. Note that this force is commonly called the weight. This weight, mg, is different from our everyday use of the word weight, which is known in physics as mass, which is why I have the nerd bathroom scale. Because when people ask me how much I weigh, I say 825 newtons. Well, let's leave that for another time. We'll get it. So my weight is actually pounds is actually a unit of force. I don't know if there's a unit of mass in that imperial system. It's kilograms, right? Yeah. I would think Sheldon would have one of those in his bathroom. You know, Dr. Sheldon Cooper.
Yeah.
Okay, the next force that you're going to encounter is what's known as the normal force. Now, normal force doesn't necessarily mean normal in the, normal sense. The normal force is one that prevents objects from falling into whatever it is they are sitting upon. It is always perpendicular to the surface. I'm going to highlight that. As soon as the word always in there, that usually means it's important. Perpendicular. What does perpendicular mean? 90 degrees. Opposite to parallel. Perpendicular to the surface with which an object is in contact. For example, if there's a crate on the floor, then we say that the crate experiences a normal force exerted by the floor, and because of this force, the crate does not fall into the floor. The normal force in the crate points upward perpendicular to the floor. It's called the normal force because normal and perpendicular mean the same thing. So I'm going to add that to this one over here. All right? It doesn't call for it there, but I'm going to add it here, and we're going to label that Fn. N for normal. Some books will label it this way, F, and then do you guys know what the upside down T stands for?
Yeah.
Perpendicular?
Oh.
You've seen that?
All right, yeah.
You know, yeah. F perpendicular?
Sorry to hear that.
Okay, so perpendicular. Now, is the normal force always straight up?
Yeah.
Okay, got a yes and I got a no.
Yes.
It says that the normal force is always perpendicular to the surface.
So no.
Always perpendicular to the surface with which your body is contact. For a body on a sloping surface like a ramp, the normal force acting on the hill is still perpendicular. So here it's like that. Now you're not gonna see a whole lot of that in grade 11, but I just let you know future.
So Mr. Bennett's answer was yes? Or no?
Normal force is not always up. It's perpendicular to the surface. Okay? So on the next page, I think you have that, right? And we label it, I use it Fn. Fn for normal. Okay, friction. Related to the normal force is the frictional force. The two are related because they are both due to the fact that the body is in contact with the surface. Whereas the normal force was perpendicular to the surface, the frictional force is parallel. Parallel. Furthermore, friction opposes motion, so its vector always points away from the direction of movement. Friction is always opposite to the motion. Now, here's something that, all of this is sort of relatively simple, relatively stuff you've sort of maybe glimpsed before. Here's the first real new thing that I'm going to show you. Friction is divided into two types, static and kinetic. They are represented by FF. By the way, the big F stands for force, and the little f stands for friction. So when I go Fn, that's force, normal, Fw, force, weight, right? So the F stands for that it's a force. The other letter is what type of force it is. Okay, so FF is for friction, with a further subscript, S for static friction, or K for kinetic friction. As its name suggests, static friction occurs when the body is not moving with respect to the surface. So if I'm pushing on the lady's table here at the front and I'm just lightly pushing, it's not moving, right? Static friction. If I push really hard and it starts to move, then we're talking kinetic friction. Kinetic friction occurs when the body is sliding over the surface. Of course, rolling objects experience friction as well. Rolling friction is actually quite complicated. We're going to assume every time something moves, we're talking about kinetic friction. Sliding. Okay, rolling friction is hard. Now, friction is usually approximated as being proportional to the normal force. That is, the bigger the normal force, the more friction there is. Think of it this way. If I go and stand on the scale, right? Right now the scale weighs maybe what? How much? Maybe 20 newtons. Okay? I push it and it goes pretty far, right? Come stand on it, Zach.
Self-conscious.
Oh yeah? Well, we'll just say it newtons, so no one will know. Fair enough.
Ouch. That's big.
Okay, now if I give it a push, right? Same push doesn't go anywhere. How come? Yeah, that's good. How much? A little under 800 newtons. You're fine. How come with the same push it didn't move? Because I've made it more massive. It weighs more. The normal force is more, which increases the friction. Jared, give him a snack over there. Wake him up. Okay. Get your glasses off. Your eyes are 3/4. Oh, it was a slow blink. The proportionality constant is called the coefficient of static or kinetic friction. The coefficient is represented as mu s for static friction and mu k for kinetic friction. So this is something you've never seen before. It's the Greek letter mu. Mu. In English we spell it mu. In Greek they spell it mu. It's a letter. The Greek letter M. It's an M. It's the Greek version of M. Josh will confirm at home. Would you do that for us, Josh? I think it's M.
Yeah, it's M.
You know what I want to know? I want to know what letter they use for coefficient of friction in Greece. Do they use mu or do they use like?
Yeah, I can tell you right now they pronounce it wrong because Josh is
Is he?
It's me.
It's me. Really? But like it's not just me that's mispronouncing.
It's not pronouncing you, it's pronouncing me.
Really?
It's the
That's it, I quit. I'm going home. Really? Am I well, I don't know. I've been taught for years it's mu. Okay. You just sit over there and you laugh at me. I'm going to. Yeah, I want to know. Okay. I'm going to keep calling it mu until mu. The numerical value of mu depends on the nature of the service in which the body is accounted. So we're going to talk more about mu. I can't say talk about me. That isn't.
We understand now. That's what you explained it.
Yeah.
Yeah.
That's going to be really hard for me to change. Interestingly enough, that came up in the day when I talked about changing your belief system. Right now my head is... Okay, so I'm going to put friction force right here. Which way is this object moving? Moving right. Because friction is opposite the motion. Right? Okay. Push and pull. Another force that may act on an object could be any physical push or pull. Hang with me, you guys. I got a couple more to do. Hang with me. I know it's long. It's a long period. This could be caused by a person pushing a crate on the floor, a child pulling on a wagon, or in the case of our example, the horse pulling on the carriage. We're going to label the applied push or pull with an FA, applied force, FA. Now, it could be tension. Tension in an object results if the pulling force acts on its end, such as on a rope used to pull a boulder. If we say our carriage is being pulled by a bar, by the horse at the front end, then we can add this force to our FBD. So you'll notice here that we've got FA. Some textbooks and people get all fired up about whether it's an FT or a T for tension. Jimmy cracked corn, I don't care, it's an applied force. Call it FA and you're good. Now, in that case there, would you say that the applied force is greater than the friction force? Yes. Excellent. So are the forces balanced? No. What's happening to the object?
Accelerating.
Some people say it's moving. One person said it's accelerating. Could it be moving at a constant speed? Think, careful, think.
No.
Could it be moving at a constant speed? Braden, listen. Jared, was it you?
Acceleration. Yeah.
Why do you say it's accelerating?
Because there's more pull on one side.
Yeah. The forces are unbalanced. There is a net force, and forces cause accelerations. Jared is correct. It must be accelerating. Must be. Okay, ready to do some examples? I got 4 here, and then you're going to do some on your own. The child next door wants to take his German Shepherd named Spot for a ride on a sled. He chases Spot, who's running away, while dragging his sled behind him. What forces are acting on the sled? So the forces we talked about were gravity, normal, friction, push, or pull. So, number 1, since the question does not state otherwise, we're going to assume it's happening on Earth. So we include gravity, FW. Number 2, the sled is being dragged in the ground, which we can take to be another surface. This surface exerts a force on the sled, preventing it from falling into the ground. Thus, there is a normal force, which should be balanced. Should I get a ruler out and measure the length? No, but you should be able to draw 2 lines that are reasonably close together. Number 3, because the sled is in motion and the surface with which it is contact, the ground, does it say anything about snow?
Or two.
Yeah.
When it's still hot.
Even if it was snow, right? And you have to be careful here, okay? If it says hard-packed snow or something like that, or ice, they mean frictionless. If they just say snow, as you all know, running through the snow is a lot of friction. Yeah, there is. A little bit, right? Yeah. Negligible. So we're going to say there is friction here. So we're going to put friction like this. We tend to live in a left-to-right world. When we don't know, we tend to make things go to the right because F, friction force. FF, friction force. I was just saying, because we tend to think things moving to the right, so because it's moving to the right, the friction is to the left. Does it have to be? No.
Wait, why?
Why what? Why is friction opposite motion?
We all know.
Right? If you're pushing this way
Yeah.
and it's moving, which way is friction? Opposing motion. Friction is always opposite. Right? Always opposite. Okay, now the kid is pulling on the sled. There's a pull force and applied force. Usually it doesn't say so it's likely like that, but it could be, and you're going to see this a little bit later, you're going to see them at an angle like this, right? Like if the kid's tall, right? It would be longer, yeah, could be, right? But that angle matters. It doesn't give me an angle in the question, so. Well, is this kid accelerating? We don't know, right? Yeah, we don't know. If the kid was accelerating, it would be longer. Generally, people don't accelerate the entire time. There's a short little bit of acceleration, and then people walk at constant speed, right? So, I'm not going to worry too much about that just now. We don't know.
I thought the longer the line was more.
Absolutely. The longer the line, the more force. That's true. Okay? But if they're the same, it just means that it's moving at a constant velocity. Right? Okay. Dot and Spot. Spot, the German Shepherd, is being walked by his best pal Dot, the Siamese cat. Actually, Dot is pulling Spot across the rink and disturbing the neighborhood hockey game. What are the forces? Again, we got gravity. We're on a surface, so we got a normal force. Ice, we're going to assume is frictionless. Okay? And the pusher, it says here, the pusher pull may be misleading. While it's true that Spot is being pulled along by Dot, this is not the force acting on Spot because Dot is pulling on the rope, blah, blah, blah. Who cares? It's just an applied force. Okay? Again, some people might get excited about it being a tension. Okay? But all it is an applied force. You guys, you're making it too complicated in your mind. It's just an applied force. It means the cat is pulling on the dog. That's all it means. There's a force to the right. There's an applied force to the right. Okay. 2 more to go. King Kong's pendulum. While climbing the Empire State Building, King Kong peeks into one of the corporate windows, sees a poster with Tarzan swing. Hang with me, you guys. I need about like 2 or 3 more minutes of you listening. While climbing the Empire State Building, King Kong peeks into one of the corporate windows, sees a poster with Tarzan swinging from a vine. Our furry friend decides he'd much rather be swinging from vines instead of hanging around with skyscrapers. When King Kong is swinging from a vine, what forces are acting on him? On Earth, gravity. Is there a normal force? No normal force. He's swinging from a vine. There is no surface holding him up. There is no air resistance. So all you've really got is, in this case, you probably should call it a tension. You could make it an applied force. It's a rope, Danielle. It's just, okay, you're making it way harder than it needs to be. Maybe I am too. Right? Would those forces be balanced?
Yes.
Because he's not accelerating up or down, right? Now, if he's swinging back and forth like this, like a pendulum, there might be a little bit of air resistance, right? But really, that's all we're talking about. Okay? All right, last one, and then you're going to try some. The elevator. Our furry friend King Kong has had enough of monkeying around, has returned to the Big Apple. Once again, he's up to his tricks with the Empire State Building. Only this time, he's taken the elevator instead. While he's riding up to the top of the building at a constant speed, what forces are acting on it? So, gravity. He's standing on the floor of the elevator, so there is a normal force. Now, I think you agree there's no sideways force, but he's rising at a constant speed. So don't I need like some Do I?
Other, more line of
Okay.
Rising at a constant speed. This is back to the original statement of Anna and Noah. That one was going sideways, right? If he's moving at a constant speed up, constant speed means the acceleration is
same.
0, which means the net force is 0, which means the forces must be equal. That, my friends, is it.
I got it.
There is no applied force. Why? It's already moving. Okay? Already moving. I realize that's a little counterintuitive.